I recently learned about the language called Cowgol, which is a language designed for generating code for low-powered devices like old 8-bit computers that I think is very interesting. So it can generate code for the 6502 CPU and also for the Z80 CPU. And I'm going to take a look at the language and try to make some code that runs on a ZX Spectrum. And then I'll run that in an emulator and see how that looks. We'll of course start with Hello World. And this is what Hello World looks like in Cowgol. We use the built-in print function, or it's not built into the language, but it's built into the sort of standard library that Cowgol comes with. Print Hello World and \r is the carriage return character, which the Spectrum uses to signify a new line. So this should be a complete program that prints Hello World. I also made a make file that makes it easier to both compile the code and also look at the result and run the result as well. And this can build a binary file. Since the source file is test1.cow, I'll make test1.bin. And that runs the command line to compile the code. As that is taken from the Cowgol README. So now we have a file called test1.bin, which is 84 bytes. We can look at the hex dump to see the code for it. And we can also disassemble it. I made a make target for that as well. I just write make disassemble. And I can look at the generated Z80 code for that. I've also created a make target for running this code in an emulator. It will create a tape image file and then launch the emulator and load that tape file into the emulator. So if I type make run, it will load Fuse, which is a Spectrum emulator. It will load the code and then run it, so it prints Hello World. Let's try something a bit more advanced. And as I'm mostly into demo scene stuff on these old platforms, I'm mostly interested in hitting the hardware directly and not using built-in functionality like print statement and stuff like that. So let's write directly to the screen memory instead. And as you might know, the Spectrum doesn't have any character mode. The only graphics mode it has is a bitmapped mode. It's 256 times 192 pixels, but the color resolution is just 32 by 24 blocks because it's made for. I think that it's designed for printing text, but it's actually a graphics mode. So let's update one of these color attributes, one of these 32 by 24 color blocks that the screen contains, and those are located at the address 0x5800 hexadecimal. That is. So we want to write something into that address, and that will change the color of the top left of the top left character of the screen. So I want to declare a variable. Let's call that variable attributes. And I want it to be a pointer to bytes. And this is the syntax for a pointer to if you type within brackets, it means it's a pointer or an array. So this is a pointer to an unsigned 8-bit int, basically, yeah, a byte. And we assign that 5800, and we need to cast that to a pointer, otherwise it's treated as an integer. And to assign something to a pointer, you use the array syntax. You use the zero as a subscript to assign something to that value. And the color format is, there are 3 bits of paper color, that is the background color, and 3 bits of ink color, which is the character color. And 3 bits plus 3 bits, that sounds like something that is where you can use the octal numbers to specify. So let's use the 0 syntax for creating an octal constant, and let's use the green paper color. Color number 4 is green, and let's use a blue ink color. So this code should update the color of the screen's top left corner. Yes, it does. So this has a green background color, and if there were any text on this, it would have become blue. I can prove that as well. Let's use this address instead, which will be the second row. So there you have it. I can disassemble this to have a look at what the generated Z80 code looks like. And this tiny program generated this code. Let's dive into it. It starts with a jump to the very next instructions. That's a pretty pointless jump. It's there because if I had defined any functions, it would skip past those functions and jump straight to the code. This line here, that is from the standard library code that does this. It saves the value of the IY register because that's used when printing text. We can actually remove that. Let's not link with the library code. Just remove those dependencies and disassemble it. Make test1 a bin. Then the code becomes much shorter. Because now it only contains this code that I wrote. So it loads 5820 into the HL register. So this value 5820 is put into a 16-bit register that the Z80 has that's called HL. And then it saves the value, it stores the value from HL into the memory address 6011. And that's right after the return statement. So that's right after the code of right after the machine code. And so the 6011, that memory address is used for the attributes variable. And since attributes is a pointer, it's a 16-bit number, so it's stored at the address 6011 and 6012. And that's stored here. Then we load 21 hex into A, that is the value 41 in octal. And then we'll read the value from 6011. So we get the value from the attributes variable, put that into the BC register, and then we store the value in A into BC. So that corresponds to this assignment. The BC register has been set to point to contain the value of attributes, and this assigns the value to the memory address that BC points to. Let's try something more advanced. Let's try to fill the whole screen. From the top left corner, 5800 is the address for that. And we have to create a loop for that. I'll use the variable I as a loop counter. And the screen is 768 bytes, that's 300 in hex. So we need to fill the 300 bytes. We need to define that this is a 16-bit value. It won't fit into byte. So it's an unsigned 16-bit int. And loop while I is not 0. And do the same thing as we did before. Put the value 41 into the address pointer to by attributes, and then we increase attributes by 1 to point to the next address, and we decrease. Oh, sorry, there is no such syntax in Cowgol. You have to use this assignment syntax instead. And decrease y, I equals I minus 1. And I think the syntax is end loop. Let's see what that does. Nope. Is the syntax something like this, maybe? Oh, I think that is the syntax. Yep, that seemed to have filled the screen. It's a bit hard to say because the Spectrum Basic prints changes these two bottom rows into white to print this this success message. That is the input area that the Spectrum uses. You can create an infinite loop in the end, just so it doesn't return to basic after running. So that filled the whole screen and nothing but the screen. We can prove that it didn't fill more than the screen. This is something I have to do to see if there's an off by 1 error somewhere. Yep, that worked. It didn't fill the whole screen when I decreased the value by 1, so that was correct. Let's look at the disassembly of this. The interesting thing here is that it loads the value 5800 into HL, the value 300 into BC, that's two of the 16-bit register that the Z80 has, and stores them at 6032 and 6034 respectively. So 6032 holds the attributes variable, 6034 holds the I variable. The interesting part here is that there seems to have been some kind of optimization or something done by the compiler here, that it used both the HL and the BC register and interleaved the initialization of them and storing their values. Anyway, in the end here, there's a loop jump back to 6010, and these labels are generated by this Z80 DASM program that I use. It generates labels when it sees that there is an instruction that accesses that location. So because there is a jump to the address 6010, it will print a label at that address. That's a pretty nice feature of this disassembler. So the loop obviously starts here, and then it loads the value from 6034, which we agreed was I. And here it checks whether HL is 0 by taking the high byte, that is the H register, and the low byte, which is in the L register, and OR them together. Because if the logical OR of the high byte and the low byte is 0, then the whole of HL must be 0. And if that is the case, it will jump to 602F, which is after the end of the loop. And here's the infinite loop. It just jumps back to the same instruction again. So that corresponds to this infinite loop here in the end of the code. So it loads the value 41 octal, 21 hex into the A register, gets the value from 6032, the attributes variable, and stores the value of A into that address. So that corresponds to this line. Then it loads the value from 6032 again into HL to increase it. So it loads the value from 6032 and then increases it. So that corresponds to this. It loads the value from the attributes variable, increases that by 1. So that, and then actually a bit later it stores that in memory. One interesting thing is there that even though there is no plus equals operator in Cowgol, it's realized that this just increases the value of this variable by 1. So it generates an inc instruction, which is the fastest way to increase a value by 1 on the Z80. Actually, I'm a bit curious. What happens if you increase it by 2? Will that compile into an add instruction, or will it be 2 inc instructions? Let's see. Yep, that compiled into 2 inc instructions. That's still faster than trying to add a value. If we add 3, what happens then? There will be 3 inc instructions. Where is the limit to this? Even 4 inc instructions. And by 5, it uses the add instruction, and that requires 2 registers. You have the value to add 2 in HL, and the BC register has to contain the value 5, because there is no immediate format of the add instruction for 16-bit instructions, for 16-bit registers on the Z80. So you have to add one register to another, and that other register is always HL. So add HL, BC. And there's some other things going on. Suddenly it starts using the DE register as well. Okay, let's go back to the original one that just added 1. And look at the disassembly for that. Next step here is that now we have done this line. So next step is decreasing I by 1. So we load the value from 6032, which is the memory address containing the I variable, decrease that by 1, and then we store the values from it into memory again, and then jump back to the beginning of the loop. As you can see, there are some pretty simple optimizations that I think later versions of Cowgol will do. You can see here, for example, that we load the value from 6032 into HL twice. The second load is unnecessary because the CPU just 2 instructions above did that. And also you could maybe optimize it by not using the memory addresses as much and storing more of the values in registers. But that's pretty difficult to do on a Z80. So it's still pretty good code. This was just my early impression of the language as it is as of today. It's an ongoing project, so David is still working on it and making improvements from time to time. And I'm really looking forward to see where this project is going and see if I can use it for anything in the future.